Hi, my name is Aryan Potar. This is my lab report for Physics 2211 at Georgia Tech. This lab investigates the universal law of gravitation. First, I'll state the purpose of the lab. Then I'll introduce the system and its surroundings. I'll then explain key concepts such as Newton's second law and gravitational force. This lab is divided into two parts. The first part focuses on estimating the mass of a black hole using a computational model. The second part focuses on predicting the motion of a spaceship near the black hole. I'll then proceed to answer essential questions. The first part of the lab aims to visualize gravitational force and use Newton's second law to calculate the mass of a black hole. In this part, the system in question is a star that is orbiting around the black hole, and the surrounding is the black hole itself. The second part focuses on determining the initial velocity of a spaceship launched from a nearby orbiting planet in order to get close to the black hole without crashing into it. In part 2, the system in question is a spaceship, and since the orbiting planet and the black hole both exert a gravitational force on the spaceship, they make up the surrounding. Summary of results. Through the investigation, the mass of the black hole was determined to be 1.3 into 10 raised to 34 kilograms. The initial velocity of the spaceship should be about negative 3.5 into 10 raised to 7 in the x direction, 4.5 into 10 raised to 6 in the y direction, meters per second. The rate of change of momentum is expressed as dp dt, where p is a momentum vector. Any vector can be represented as a product of its magnitude and unit vector. We use this fact to differentiate the momentum vector, yielding us an equation with two components. According to Newton's second law, the net force acting on an object is equal to the rate of change of momentum. Hence, F net is equal to dp dt. By the equation on the left, it is apparent that these two terms are basically just the perpendicular and the parallel components of dp dt. Hence, we can then use this to calculate the parallel component of F net and the perpendicular component of F net as shown on the right. Since F net is equal to dp dt, the magnitude of F net is equal to the magnitude of dp dt. In part 1 of the lab, it is assumed that the only force acting on the star is the gravitational force exerted by the black hole. Hence, we can equate F net to F gravitational. We can also assume that the magnitude of F net is equal to the magnitude of gravitational force, yielding the equation on the right. The magnitude of dp dt is equal to the magnitude of the gravitational force. We can then rearrange this equation to find the mass of the black hole. Computational model to predict the mass of the black hole. The mass of the star was set to 2 into 10 raised to 30 kgs. Delta T was set to 86,400 seconds, which is the number of seconds in one day. I then used xval and yval to calculate the v initial and v final, which are then further used to calculate initial momentum and final momentum vectors. Delta v was calculated using v final minus v initial, and delta p, or change in momentum, was calculated using p final minus p initial. I then used some simple vector calculations in algebra to calculate the perpendicular and the parallel components of F net. The second part of the lab focuses on mapping the motion of a spaceship that goes as close as possible to the black hole without actually crashing into it. For this part, I used trial and error and basically played around with the x and y components of the spaceship's initial velocity. The surrounding in this case consists of the black hole itself, as well as a nearby orbiting planet from the surface of which the spaceship is launched. Hence, the net force acting on the spaceship is now the sum of the gravitational force exerted by the black hole on the spaceship, as well as the gravitational force exerted by the planet on the spaceship. The motion of the spaceship was mapped using position update formula and velocity update formula given by Newton's second law. Discussion questions. So what are the differences between the net force and the rate of change of momentum and the respective parallel and perpendicular components? Mathematically, there are no differences, they are equivalent, and this is also seen by the formulas derived earlier. However, in this lab, the major difference is that the change in momentum can be calculated easily based on direct observation of the object's position, velocity, and momentum. However, the net force is something that we cannot calculate without knowing the mass of the object. What if we wanted the spaceship to enter an orbit around the black hole? In my opinion, we have to reduce the magnitude of the velocity so that the spaceship is bound to the black hole. Potential errors to consider for this lab include rounding errors, misinterpretation of values, as well as errors associated with the trial and error method.